Hi everyone. Welcome back to Dave's Math Channel. I'm your host David Tear. Today I'm going to talk about higher dimensions. I think this is going to be a pretty long video. I'm going to talk about higher dimensions both in math and in physics. And you'll see that there's a lot of physical applications of higher dimensions and even non-integer dimensions, which are also known as fractals. I talked about those in another video, but I'm going to kind of summarize everything that's pretty well known about different kinds of spaces with different numbers of dimensions. So let's begin. All right. Well, actually, you can have zero dimensions. I didn't mention that, but a point has no dimensions. It has no extent. It's just one single point, or even a set of points has no dimensions, because you can't move anywhere from one point. But so that's a zero-dimensional thing. And then the next higher dimension that's pretty obvious is a line. A line has one dimension, and a dimension is just kind of like a degree of freedom. It's a direction in which you can move. So when we say that a line has one dimension, all we're really saying is there's one number, which we usually call x on the real axis. This is the real number line, and real numbers are a one-dimensional set, meaning that there's one number, one real number. It doesn't have to be real, but in the case of real numbers, it is a real number. And that's our degree of freedom. We can choose any number we like for our position on this line. So we can move around that line, this number line. That's why it's called the degree of freedom. Not very exciting yet. You can only move around in one dimension, but you can move up to two dimensions. Then things get a little more interesting. I mean, this is the Cartesian grid. This is like the x. It's also called the XY plane. So I just mentioned how you can use one number, which we call x, for one direction, which is usually drawn as a horizontal line. Well, you can add a second direction, a vertical line, which is exactly what Rene Descartes did. He's the one that came up with this in, I think, 1637. This is called the Cartesian plane or the XY plane, if you like. And you can see that if you want to locate a point on this plane, you need two numbers now. So now you have 2 degrees of freedom. You can control how far you move to the left and right. That's one dimension, and you can control how far you move up and down. That's your second dimension. Kind of like flatland. I probably should have mentioned flatland in this video. It's an excellent novella. It was written in the late 19th century, I think in 1880, by author named Edward Abbott. I believe it was the only book he ever wrote, or at least it's the only one he's really famous for. I highly recommend it. It's a very good book, and the book Flatlands about he imagines that there's this two-dimensional world, which he calls flat. Man, he even imagines these kind of polygons living in this world. They're like, I guess they're the beings in this world, and it's not just about higher dimensions. I mean, he talks about higher dimensions too. He talks about how ridiculous it is that we don't believe in 4 dimensions. I think when he wrote the book, most people didn't. Uh, but he kind of gives the analogy of being as in a two-dimensional land, which he calls flat land, not being able to imagine a third dimension or even higher dimensions. He kind of makes a very convincing case for the existence of higher dimensions. And not only that, but he also ridicules Victorian society and it's a pretty satirical story, but it's a very good story. Anyway, enough of that. So the Cartesian plane is like a flat land with 2 dimensions. And then you can move to 3 dimensions. Actually, before I do that, notice that these are what are called Cartesian coordinates, also known as rectangular coordinates. Because the grid looks like a rectangle, right? It's a rectangular grid or a square grid. So you can move in sort of two orthogonal perpendicular directions, if you like, left and right and up and down. But you don't have to move in those particular directions. There's also a thing called polar coordinates. So you can identify points in 2 dimensions in another way. Actually, there's infinitely many. These are the two simplest, but this is called polar coordinates. So you don't have to use, x, y, how far to left and right, x coordinate, y coordinate. You can use what are called polar coordinates, those include the radius r, usually written as r. That's how far you are from the center, the origin. And we still have an origin in the xy plane. That's just a point in the middle. But you can think of that as like where everything's centered, and then you can, measure how far out you're moving. That's your radius, and also the angle you're moving about it. That's usually written as theta, sometimes phi. So in this case, they show a point with polar coordinates. It looks like r equals, they show a bunch of them, but I guess the point with this arrow here, it looks like 1, 2, 3, 4, 5, 6, 6. So I guess they're showing r equals 6 and theta equals 4 pi over 3 in radians, which is the same as 240 degrees. So that just shows you that you can also write points in another way. And there's actually infinitely many possible coordinate systems. This is just another one. So anyway, that's how you can do two dimensions. And really, the important thing about two dimensions is you need two numbers to specify where you are. And this is kind of true if you're doing geography, like if you're looking at the streets in a city. And there's different kinds of cities. I mean, some cities have kind of a rectangular layout of the streets. I think most American cities do. Chicago does. You can kind of, Chicago is a good example of a two-dimensional kind of rectangular or Cartesian plane because all the address numbers are centered at, I think it's on State Street. There's like State in Washington, I believe. That's kind of the origin of the coordinate system for the streets in Chicago. And then all the street numbers are kind of how far north, in one direction or how far east or west of, they call it the loop. I used to live on 1369 East Hyde Park. So that was 13, I guess 14 blocks east of the loop. And Hyde Park, it's really 51st Street. The I guess the numbers in the other direction were 5100 south, so that would be 51 blocks south of the loop. So that's the kind of layout of Chicago. But there's other cities that have like more of a polar layout. I think Washington D.C. does. Everything's kind of centered at the. I don't know how, but there are different cities that have different kinds of geometry in the streets. So I just thought I'd point that out. But if you're not interested in your height, if you're just interested in where you're located in a city, then you need two numbers, and that's why a city or any region on the surface of the Earth is two-dimensional. So, but then you can go to three dimensions. It's kind of a picture of a three-dimensional grid. It gets hard to draw pictures because you're drawing on a two-dimensional surface, but you can picture in a mind three dimensions. We live in three dimensions, so I don't think we have a problem imagining three dimensions. And to continue with the analogies of cities, it's not enough to just know how far north, east, south, or west you are of a given point. You also have to know how high you are. So if you live in an apartment complex, you usually have to say what floor you're on, right? So that's the third dimension, height, if you like, or they usually call that z. So x is like, I guess that would be horizontal, that would be east-west, y would be north-south, z would be up-down. But so we live in three dimensions, and it's kind of hard to imagine more than three dimensions. But mathematically, it makes perfect sense to define as many dimensions as you want. You can define infinitely many dimensions. You can even define continuum of dimensions. I'm not going to get into that right now, but and then I thought I might. So while we're talking about three dimensions, I mentioned how you can have polar coordinates in two dimensions. You can have kind of the equivalent of polar coordinates in three dimensions. These are called cylindrical coordinates. So you have, it's like polar coordinates in the xy plane, but then you still add the z axis, the same z axis you had for rectangular or Cartesian coordinates in three dimensions. And not only that, you also have spherical coordinates. These are useful if you're describing points on the Earth. You want to know the latitude and longitude. Those are angles about. There's actually two angles in spherical coordinates. There's what's called the azimuthal angle. That's phi. That's the angle in the xy plane. That's kind of like the polar angle. But then you can add a second angle, and that's called the polar angle for spherical coordinates. That's what they call theta here. That's the angle. That's actually latitude or co-latitude. So you can think of phi as a longitude, and longitude on Earth is usually goes, I guess, the other direction. It goes clockwise, but mathematicians like to go counterclockwise. So phi is kind of like the negative of longitude, and theta is kind of like they started at the North Pole instead of starting at the equator. So yeah, it's actually 90 degrees minus your latitude, or pi if you want to use pi over 2. If you want to use radians, it's pi over 2 minus your latitude. That's kind of called the colatitude or the polar angle. But anyway, the point is that you can still use three numbers to represent a point in spherical geometry. Not only did it represent points on a sphere, that's theta and phi, but you also need r if you want to know how far you are from the center. And these are conversion formulas. They're kind of complicated, but you can convert if you have any kind of two coordinate systems that are both defined mathematically. You can have conversion formulas from one system of coordinates to another, and they do that here. The top three equations on the right, they'll show how to go from spherical coordinates to rectangular coordinates in 3 dimensions. The ones on the bottom show how to go the other way from rectangular to spherical, which are very useful formulas. And you don't have to stop at 3 dimensions. So here's where we get to higher dimensions. I mean, just because we can't really visualize 4 dimensions, we can define them mathematically. And there's these are called hypercubes. I mean, a 0 dimension. I didn't really talk about 0 dimensions, but a point has 0 dimensions. You extend it in one direction, you get a line segment. So you extend it, say I don't know, 1 meter, and then you get a line segment of length 1 meter. That's a one-dimensional space or manifold, if you like. And then you can move it in a perpendicular direction. You keep going perpendicular directions. So you've stretched the point on the x-axis, and now you can stretch the line segment in the y direction. Now you get a square that has 2 dimensions, and you can keep doing this. So now you can stretch your square in a third direction. I guess here is depth. That's our third dimension here, because we all have this square in the xy plane. Now we have to kind of move orthogonal to the plane, and you have to just imagine that because they're drawing it in 2 dimensions here. But it's pretty easy to imagine because we've all seen cubes and we live in 3 dimensions. So then you get a cube, which is a 3 dimensional analog of this figure, and you can keep going. I mean, we can't go in the space we live in, but you can imagine that maybe there's a fourth dimension, a fourth spatial dimension, that you can move the whole cube in that direction. And if you did that for the same distance, you would get what's called a tesseract, which is another name for a 4-dimensional hypercube. And of course, you can keep going as many times as you want. Just keep imagining there's other directions you can move this thing and keep doing that. And mathematically, that makes perfect sense, although it's very, very difficult, next to impossible, to actually visualize these things. And this is kind of an interesting visual. I don't know how many guys saw the movie. What was it called? Interstellar, I think, came out about 10 years ago. There was a scene in that movie that looked kind of like this. I think the guy who did the kind of the scientific research for that movie that went into the production. He's actually a pretty famous physicist. What was his name? Can't remember his name right now. He's pretty famous. I'm kind of embarrassed I can't remember his name right now. Jeez. Anyway, he did the artwork for that movie, and he imagined what it would look like inside a tesseract. This is supposed to be the interior of a 4-dimensional hypercube, also called a tesseract. And I think there wasn't a scene in the movie where they went into a tesseract that looked kind of like this, and it was kind of weird because they could see themselves through it. They could look through time. They could look through the fourth dimension, basically. Yeah, kind of cool and kind of mind-boggling. But what the hell is this name? I'll think of it. So when I think of his name, I'll say what it is. Maybe you guys know. But anyway, so yeah, now I'm getting into physics. So what can we say about the physics of higher dimensions? So far, I've only talked about the mathematics of higher dimensions, but actually, it turns out that higher dimensions are important in physics as well. And I think one of the first people to point that out was Einstein, also Minkowski. Minkowski actually came up with a geometry that Einstein used for his theory of relativity, and it's called Minkowski space-time. So you're supposed to imagine the fourth dimension is time. And it doesn't work quite like the three spatial dimensions. That's where it's kind of different from, it's not Euclidean space. I mean, the spaces I was talking about before with the tesseracts and the hypercubes, that's what's called higher dimensional Euclidean space. That's the space where you treat each dimension the same. You say they're all spatial dimensions. And as it turns out, time doesn't behave quite the same way as space. In some ways, it does. I mean, the weird thing about Minkowski space-time. So this is a picture. Okay, I have to say what this picture is about. So here's what you're supposed to imagine. You have these things called light cones, and I guess I have to explain what that means. So this is what's called the block universe. So what is this? What do we mean by this light cone? Imagine you're standing here. So imagine these two dimensions, this plane in the middle. Think of that as space. I mean, because we're limited by the number of dimensions we can represent in these pictures, they show it as two dimensions. But imagine it's really a three-dimensional space. So just imagine that this middle plane in this picture is three-dimensional space. They've suppressed a dimension. Uh, and then you're supposed to think of up and down as time. So time, the future is up in this picture, and the past is down. That's why this cone on the bottom is called the past light cone, and the cone on top is the future light cone. What do we mean by that? Well, we all know the speed of light is finite, right? It's about 186,000 miles per second, or in metric, about 300,000 kilometers per second. In relativity, we usually give it the value 1. We kind of define our units so that a light year is equal to a year, which means that the speed of light is 1, because we're equating our distance units to our time units. I know that sounds a little weird. We set c equal to 1. That's like what's called a natural unit of length, of speed. So we have kind of natural units of length and natural units of time, and the unit relating them is c, the speed of light, which we set equal to 1. And that's why you're supposed to imagine. So nothing can travel faster than the speed of light, which is 1. If you like 1 meter per meter, because you can measure time in meters. So you're moving out 1 meter, and light can travel 1 meter in the time equivalent of 1 meter, which is a very small period of time, about I guess about 3 nanoseconds. So what that means is that since nothing can travel faster than the speed of light, you're limited. You're kind of confined to this light cone. I mean, you're moving up through time. That's how we all are. We're all moving through time. Like a lot of people like to think of time as moving. I don't. I like to think of time as stationary and we're moving through it. Because the time is just another dimension, right? It's a dimension that we're moving up through. We don't know how to travel back in time yet. Maybe someday we will, but we don't know how to travel into the past. But we're all traveling into the future at seemingly the same rate, 1 second per second, or 1 meter time unit per meter, if you like. We're moving through time at the speed of light. Yeah, that sounds kind of profound, but we are. So think of us as moving through time. So you can think of this plane in the middle as the universe, say now, and now for me right now is, let's say today's March. March 19th. So now for me, I'm living in Las Vegas, Nevada, where it's 4:54 p.m. Pacific Standard Time. So now for me is 4:54 p.m. Pacific Standard Time. That's what this plane represents, the universe at that time, according to me. So you're supposed to imagine that we're all moving through the future. It's no longer 4:54 now; it's closer to 4:55. So I'm moving up in this picture. I mean, this picture I just said was now. It's not now anymore. It's the past. It's 1 minute in the past. So I've moved up. We're all moving up in this picture. We're moving up through this future light cone. And if we're not moving, we move vertically. We're moving exactly up along the t-axis, if you like. Remember I said the three-dimensional space has the x, y, and z axes? Well, time has a fourth axis, which we can call the t-axis. So we're moving in the t direction, or at least I'm moving in the t direction. Maybe you're driving, maybe you're doing something else. Maybe you're not moving in the t direction. Maybe you're moving a little bit at an angle. And we all can. We can all move through this future light cone. We're free to move however we want within this future light cone, but we can't move outside of it. And the reason we can't move outside of it is because that would require moving faster than the speed of light, which we can't do. And a beam of light moves at the speed of light. A beam of light actually moves along the edge of this future light cone. So the edge of the future light cone is actually the path that every beam of light has to take that had started what I called now, which was 4:54 p.m. It's already later than that now. But you know, at the time when I said that was now, that's when all the light beams were traveling from where I'm sitting right now. Every light beam that was leaving from where I said was now at that time is moving along this future light cone, different directions. It can move in three possible directions. According to this picture, it looks like only two, but all the light beams can move out from a sphere. They're all on this sphere. That's what I call the future light cone of where I was at the time I called now. Similarly, there's a past light cone, the cone on the bottom. That's where all the light beams would have to meet at the point I called now, where I was sitting. So that means that all the information I was gathering at that point that I called now, all the information I was gathering about the universe had to come to me along this past light cone at that point. I mean, now it's not what I call now, it's later now. It's about 2 minutes later. So now I'm getting information from different light cones. There's other light cones that are giving me my information. But think of it that way. All the information we all gather, all of us, all the information we're all gathering about the universe comes from all the past light cones that intersect our current position. I mean, that's where we're getting all of information from. And that's basically the whole universe, because the collection of all past light cones, they stack up into Minkowski spacetime. So that's what Minkowski spacetime is. And you know, the weird thing about it, time doesn't behave the way we think it does. One thing I didn't mention is if you were moving, the sheet in the middle would tilt. That's what's weird about it. I mean, there's no absolute time. This is one thing that Einstein proved when he came up with his theory of relativity. Time is relative. I'm sure you guys have all heard that. What exactly does that mean? Well, it means that there's no universal time. You know, Newton thought there was a universal time. Newton thought, and Newtonian mechanics is kind of based on that idea, that for the whole universe, there's a single moment that everybody can agree is the same time. You know, the time I said was 4:54 p.m. Everybody in the universe could agree at that particular time there was 4:54 p.m. And they could synchronize their watches. They could come back together and see they all said at the same time. Well, that's not true according to relativity. There's no consistent way to do that. So, you know, if I was moving through this future light cone, say I was on a rocket traveling like half the speed of light, this plane in the middle would tilt. It would tilt at the same angle that I'm tilted in this picture, so that now I would have a different perception of now. And then if I met up with you later, our watches wouldn't agree anymore. That's called the twin paradox. You know, because we don't measure time the same way if we're moving relative to each other. This is an important consequence of the theory of relativity. Time is relative. Time depends on how we're moving. Pretty profound. And if you think of, you know, if you just think of, I mean, back up and think about three-dimensional space. If you think of time as just another coordinate, this shouldn't be so surprising. I mean, we move through space, right? Our x coordinate is not fixed. We don't all agree on x. You know, I mean, if we're living in Chicago, I could be on 51st Street. You could be on 37th Street. We have different x coordinates or different y coordinates. We're not mesmerized by that. It's natural. In the same way, we have different t coordinates. We don't agree on our time. We're living in different times. And actually, that's one thing I don't like about Star Trek. There's no star date. That was a big mistake Gene Roddenberry made. There's not a star date for the whole universe. That was a mistake they made on Star Trek, and I guess it makes it easier to understand what's going on. It's easier to kind of give the whole universe a star date so you can order events on the show. But no, that wouldn't work in real life, especially if you're traveling on spaceships that can travel close to the speed of light. Another thing, I don't believe it's possible to travel faster than the speed of light. So I don't like the warp speeds. I mean, maybe there's wormholes, but that's not a warp. That's just taking a shortcut through space time. So they got several things wrong on Star Trek. I still really like it though, even though the science isn't really that accurate. I still think it's a really good show. I guess Arthur C. Clarke is one of my favorite sci-fi authors because one thing Arthur C. Clarke did, he made a point in all of his sci-fi stories of making sure that all the science that it goes into his stories is real science. He didn't come up with any fictional. There's no. I don't think there's any books by Arthur C. Clarke in which anybody travels faster than the speed of light, and he doesn't assume there's a universal time, and so he gets it right. He gets it right with his science, and that's one thing I like about him. I just thought I'd point that out. Like I said, I still really like Gene Roddenberry. I like him a lot better than George Lucas. I'm not as much into the Star Wars movies. I mean, they're fun. They're fun, but that's more fantasy than sci-fi. The science in the Star Wars series is even worse than the science in Star Trek series, I think. And I think the philosophy is too. I'm more of a Trekkie than a Star Wars person. I just thought I'd point that out. Anyway, let's continue. So these formulas were called the Lorentz transformation formulas, and this is just more of what I was saying, that space and time behave differently than we expect in relativity. Time, they kind of rotate with respect to each other. You can think of this as like a rotation through time in a way where you have x prime and t prime related to x and t, and you can think of this kind of like a rotation that depends on how fast you're moving, but it's not really a rotation. It's more like a shear. The axes actually kind of approach each other. They don't actually rotate with respect to each other. Like I said, time behaves a little bit differently than the three spatial dimensions, but and then we get into general relativity. This is where things get really complicated. This equation on this slide, I think this is one of the most amazing equations I know in physics. This is Einstein's equations of general relativity. I talked about these in another video. I'm not going to try to explain this formula, but it's really the formula or the set of formulas. This is a tensor equation, so it's really better to think of it as a set of formulas than one formula. But this equation or set of equations basically tells you everything you need to know about general relativity, which is the kind of modern theory of gravity. Kind of everything in it you have to know about everything big in the universe. It doesn't include quantum mechanics. It's the only thing it doesn't include. Pretty amazing formula. Explains gravity, black holes. It explains time dilation, everything in special relativity. I'm not going to go into it in any more detail, but what's the upshot of this formula? I mean the I was talking about Minkowski spacetime. Minkowski spacetime is flat. Okay, you should think of Minkowski spacetime kind of like Euclidean geometry because it's almost Euclidean. The only difference is time behaves a little bit differently than space. But we all know Euclidean geometry is flat, right? But we also know that there's curved geometries, like the geometry of a sphere or a hyperboloid. I mean, a sphere has what's called positive Gaussian curvature. A hyperboloid has negative Gaussian curvature. Those are non-Euclidean geometries that were discovered in the 19th century. And you can actually extend that to four. You can expand that to space time, and then you get curved space time. And I think that this is what general relativity is all about. Special relativity deals with flat space time, Minkowski space time. But we all know that space time is not flat, and as a matter of fact, it's the curvature of space time that is really pretty much the same thing as gravity. Gravity is nothing but curvature. four-dimensional curvature of space-time. And that four-dimensional curvature is given by the name of the Riemann curvatures tensor, r mu nu, this tensor on the left side of this equation. There's also something called the Einstein curvature tensor, written as g mu nu, which is just this quantity on the left. And like I said, I shouldn't go into this anymore, but this is the equation of general relativity. Um, uh, anyway, yeah, I probably should have. Yeah, and if you look at this picture below, this is a kind of a space-time diagram of a black hole. So this is an analogy that's often used in general relativity, the rubber sheet analogy. So a plane is a flat sheet, and if you put a ball on a plane, it doesn't move, right? Or if you move at a constant speed, it keeps moving at constant speed. It doesn't, that's Newton's law of inertia, the first law of motion. Uh, but if you're near a black hole or a star, it doesn't even have to be a black hole. A black hole would go down to infinity, but a star would just be kind of a bulged, finite dip at the bottom of this picture. So I think you guys have probably seen this. This is what space-time looks like in the vicinity of a star like the sun or a black hole. And if you were orbiting it, like the Earth is orbiting the sun, you can think of the Earth as a ball on this sheet, and if you move the ball, you have to give it some horizontal motion, but then it'll move in a circle. And what a lot of people say is that the reason that the Earth is orbiting the sun in a circle is because it's moving in a curved region of space-time, and it's curved according to this equation on top. The rubber sheet analogy isn't perfect, but it's a pretty good analogy. So now I want to talk about even higher dimensions. So I've talked about four dimensions in physics, relativity basically. And now I'm going to talk about a fifth dimension. And there were a couple of guys, there were a couple of particle theorists in 1926, Kaluza and Klein, and they actually came up with a quantum mechanical theory that included electricity and magnetism as well as gravity. Einstein was really, really impressed by this, by the way. So remember, I said that the general theory of relativity is a four-dimensional theory. It involves four-dimensional curved space-time. Well, you can actually add a fifth dimension that also includes electricity and magnetism. This fifth dimension, it's what's called a compactified dimension or a curled up dimension. You're supposed to imagine that the circle, see the picture on top? I mean, the picture on the bottom is just a curve in four-dimensional space-time. Basic curve with zero thickness. Curves have zero thickness, but it's not really a curve. I mean, the idea of Kaluza-Klein theory, and you're supposed to imagine this curve is like the trajectory of a particle. So this would be like classical physics. But what Kaluza-Klein theory says is that particles aren't just points, they're really more like circles. So there's actually a second direction you can move on this. This picture on top is what's called a manifold, a two-dimensional manifold. You should think of it like a garden hose. So this would be like looking at a garden hose from far away, the picture on the bottom. It looks one-dimensional. But that's just because the width of the garden hose is so small, you usually don't see it until you get really up close. But you can kind of imagine your ant crawling on the surface of a garden hose. And according to the ant, since the ants are much smaller than the diameter of the garden hose, he thinks he's moving in two dimensions. He can crawl, he can crawl in a circle, around the hose, around the narrow, dimension of the hose. So the hose is two dimensional. It just looks one dimensional if you're far away. And you're supposed to think of the electromagnetic field as giving rise to this circle, this circular cross section of the hose. That's basically what the Kaluza-Klein theory says. And Einstein loved that theory, and unfortunately, it probably would have been the unified field theory if there weren't any other forces besides gravity and electromagnetism. Those were the only two forces that were known when this theory came out in 1926. But then, oh yeah, I probably should have showed this earlier. This is the rubber sheet thing. I already talked about that, but you just imagine this is what the Earth does to the space-time around it. It makes a little bulge on the bottom that, and that warps space and time. Yeah, now I'm talking about particles and uh, Yeah. So now I think I'm sort of getting a string theory. I guess I didn't put these slides in order quite, but I was talking about the Kaluza-Klein model. So you're supposed to think of particles as strings, one-dimensional things. I mean, it's pretty beautiful if you think about it. So before string theory, this is what we had. This picture on the left. This is what's called a Feynman diagram, by the way. And Richard Feynman, I mean, he was an amazing physicist. I think one of my favorites, probably one of the greatest. At least one of the greatest of the 20th century. Probably the greatest particle physicist of the 20th century. I think he came up with quantum electrodynamics, which is the quantum mechanical theory of particle interactions. But the problem with this theory, even though it was a very, very successful theory, and by the way, it was one of the most successful theories ever devised. It made predictions that were correct at 10 decimal places, which is the most precision I think we ever got from any theory of physics. But there were problems with this theory. And the biggest problem was that it predicted infinite quantities. I mean, the theory didn't like the fact that if you treat particles as points, then you get these infinities, and you have to do these tricks to get rid of the infinities. It's called renormalization. I'm not going to go into that. It's kind of it's almost like a hand waving method of getting rid of garbage in your theory, but it works. I'm not going to explain it anymore. But a lot of physicists didn't like the infinities that came from QED, quantum electrodynamics, so they came up with string theory as a way to get rid of them. And that's a nice thing about string theory. If you think of your particles as strings rather than particles, then you have a nice manifold. Your particle interaction is just this kind of weird manifold with these four necks. It's a two-dimensional manifold, but there's no infinities. So that would have been a nice feature of string theory, except string theory is not science. But string theory is horribly complicated. I mean, maybe it wouldn't be so bad if there were only two forces in the universe, gravity and electromagnetism. Then I think you would get pictures like this where the cross sections are nice circles, because that's kind of the fifth dimension. But actually, it turns out that there's two other forces. There's the strong and weak nuclear forces. And if you include those forces as well, then instead of getting like one extra dimension, one compactified dimension, you get six, I think, or maybe seven, depending on how you define your theory. So now we have these things called Calabi-Yau manifolds. I think they were originally six-dimensional. Now maybe they're seven-dimensional because we've replaced string theory with M theory, and we've actually added another spatial dimension to the theory. So anyway, we have these very, very complicated manifolds called Calabi-Yau manifolds. I think in 6 dimensions, they estimated there were about 10,000 of them. In 7 dimensions, there's like 10 to the 500. And one of the problems with string theory is that there's only supposed to be one of these for our universe. And a big question on everybody's mind is which one? Which one of these 10, when it was 6 dimensions, which one of these 10,000 represents our universe and what's wrong with the other ones? And now the question is what about the other 10 to the 500? And for a long time, maybe even still today, I don't know what these string theorists are doing. I got a string theory a long time ago, but I know one thing on a lot of string theories' minds that was bothering them is how do we predict which one of these Calabi-Yau manifolds corresponds to our universe? I think I have an answer to this. Multiverse. This is now known as the string theory landscape. These 10 to the 500 Calabi-Yau manifolds, I think that each one of them represents a universe in the multiverse. I think there's probably 10 to the 500, maybe even infinitely many, but according to string theory, there seems to be about 10 to the 500 possible universes, each with its own Calabi-Yau manifold. And we just live in one of them. We're only aware of one of these. But there's other parallel universes with other ones. That's kind of what I think is going on. I know a lot of people don't like parallel universes. I do. I do for other reasons as well as not just string theory. But and this is what's supposed to be the kind of the Calabi-Yau. So you're supposed to imagine 4 dimensions for space and time, and you got one of these Calabi-Yau manifolds at every point in space and time because there's 6 dimensions, extra dimensions, at every point in space and time. This is what you're supposed to think. There's like 10 dimensions for the whole universe. At least it was in string theory before M theory. Now it's 11. But when string theory before it became M theory, we were supposed to imagine that the universe had 10 dimensions, four big ones, the three spatial dimensions and the time dimension, and then there were six compactified or curled up dimensions, curled up kind of like a garden hose, but curled up very, very, very small. I mean, we're talking like 10 to the minus 35 meters now. So each of these Calabi manifolds, they're so small. They're what's called the Planck length, which is, I think, most physicists now think this is the smallest possible physically realizable length in the universe. Like now we kind of think the universe is discrete and that the smallest possible distance is the Planck length, which is about 10 to the 5 minus 35 meters. That's not just true in string theory, that's also true in a rival theory known as loop quantum gravity. So you're supposed to imagine these Calabi-Yau manifolds as really, really, really tiny. And I think one of the biggest problems with string theory is that it's not science because we can't observe any of this stuff. I mean, the smallest distances we've ever been able to probe is about 10 to the minus 18 meters. That's about the size of the highest energy particles we've been able to create. It turns out the higher energy particles you have, the smaller distances you have to probe to get them. That's because of the uncertainty principle. And I think the heaviest particle that we've made so far with accelerators is the Higgs boson. Maybe you guys have heard of that. Well, actually, that's not the biggest. It's one of the biggest. There's also the W and Z. Actually, I think it is the biggest. Yeah, the W and Z, I think those are like 81 and 93 GeVs. Yeah, and then the Higgs is 125 GeVs. As far as I know, I think the Higgs is the heaviest elementary particle that we've created in the laboratory in the way so far. And the size of a Higgs particle, because of the uncertainty principle, the higher energy particle you make, the smaller it is. The size of a Higgs particle is about 10 to the minus 18 meters. That's about 1,000th the size of a proton. Proton's about 10 to the minus 15 meters. So that's the smallest distance we've been able to probe so far. But these Calabi-Yau manifolds are 17 orders of magnitude smaller than that even. And we can't probe that distance. And until we can, then I don't think string theory will be science. It's not even science because it's not even wrong, because we can't test it. We can't probe these small distances, and we can't reach these high energies. So right now it's more like theology. It's kind of beautiful theology in a lot of ways, but the only kind of scientific evidence for any of this is just kind of mathematical elegance and beauty. And I mean, there is something to say for that because that's kind of how the theory of relativity was before Eddington made his first observations of the bending of starlight around the sun. So for about 14 years, even Einstein's theory of relativity wasn't science either, even though he knew it was right. But and I guess a lot of string theorists insist they're right. I don't know if they are or not. I don't even really care anymore. But anyway, that's Calabi-Yau manifolds and yeah, string theory. I don't even know why. But I kind of put these in the wrong order, I guess. But yeah, string theory involves one-dimensional things called strings, so we're supposed to imagine particles aren't zero-dimensional objects. They're not points. They're one-dimensional things, which can be open or closed. And I think all the pictures I've shown so far shows them closed, like a rubber band, but they can be open too. And now we have M theory. Yeah, here's M theory. So the reason we got M theory is because one of the problems, there were a lot of problems with string theory when they were developing the theory. I think one problem, this was the last problem I remember when I was studying it. This was back in 1986. The first string theory revolution happened in 1984. That's when everybody got all excited about string theory because it looked like it was a theory of everything. The kind of holy grail of physics. That's why everybody jumped on the bandwagon and started studying it. But a couple of years later, a lot of physicists got very frustrated because there were 6 different possible types of string theory. And there should only be one because we have one universe. So why were they getting all these 6? I mean, that almost ended the theory. But luckily, I guess I wasn't studying this stuff at the time. I think in the 90s, this was the second string theory revolution. I think this happened in 1995. So for about 9 years, nobody knew what to make of all these 6 different versions of string theory, other than they had them all. But in 1995, what they did was they came up with a new theory called M theory, in which these fundamental things weren't necessarily one dimension, but they had every dimension up to 9 or 10. And if you did that, if you allowed them to be sort of membranes or p-branes, I think they call them, p being the number of dimensions, which could be anything from 1 to 9 or maybe 1 to 10. If you did that, then you could unify all of these different versions of string theory into one single theory called M theory. So this was kind of like a unification. And I think a lot of scientists, a lot of people studying string theory got really excited about this. They thought they were onto something new. Maybe they were. I really don't know. At this point, it's still just math. That's all it is. It's just math, and it's a lot of conjectures. There's no experimental evidence for any of this stuff. Until there is, I don't even think it's science. It might be true, but we just don't have any experimental evidence to back it up. And according to Roger Bacon's definition of science and the scientific method, until you can perform an experiment to test your theory, then it's not science. So I still think string theory is not science. It might be beautiful, it might even be true, but it's not testable yet. So the M theory looks like it's pretty beautiful. I've kind of wavered in my feelings about string theory, actually. I mean, I haven't always been against it. As a matter of fact, I think I did start getting excited about it again in the 90s once I learned about M theory. I read a few books about it and I was pretty intrigued. I thought maybe they're onto something now, and maybe they are, but it's still not science. And until it is, I just I don't want to get into it. But yeah, and I was talking about I guess it is p. P can have p from 1 to 10. So I don't even know these are D brains and P brains, and there's different ways of measuring the dimensions of brains, and I don't even really know what they are. At one time I did. I think D brains are connected to another manifold. I think that P brains are closed and the D brains are open, or they're connected to another manifold. I think D stands for Dirichlet. And I think these check marks just indicate the possible combinations you can have. I mean, that's about all I know about this. But so that's enough about string theory. And what else? What else can we say about dimensions, higher dimensions in physics? Well, I think the last thing I want to talk about in that regard is Hilbert space. Hilbert space, actually, this is older than string theory. Hilbert space is what quantum mechanics is based on. And Hilbert space is kind of weird. It's an abstract space, but it's an infinite dimensional space. It's the space of what are called eigenstates. Or I don't even want to talk about what those are. But in quantum mechanics, we work with all the calculations in quantum mechanics involve calculations in Hilbert space. These are the spaces of solutions to Schrodinger's equation. I guess you can think of waves on a string. So you know how you have harmonics for a vibrating string. You can think of each of those harmonics as an eigenstate, a possible solution to the vibrating string. And since there's infinitely many possible overtones or harmonics of the string, you can think of each of those as an abstract dimension in Hilbert space. It acts just like, it's an abstract space, but the math works out where it's just like doing calculations in ordinary space, which is a little weird. So according to quantum mechanics, we live in an infinite dimensional Hilbert space, and you can even have a continuum of dimensions. I think that's all I want to say about that. Now I want to talk a little bit about fractals. Like I said, this is a long talk, and I think I'm almost done. I think fractals is the last thing I'm going to talk about today. On the top left, you might be familiar with this picture. This is what's called the Sierpinski triangle. And these other pictures here are sort of other analogs of the Sierpinski triangle. And it turns out that each of these pictures is what's called a fractal. And there's another video I made about fractal. I'm not going to go into fractals in detail, other than to say that there are spaces that actually have a dimension that doesn't have to be an integer. And I think for each of these pictures in this diagram, I think none of these have integer dimensions. I know the Sierpinski triangle on the top left has a dimension of the base 2 logarithm of 3, which is about 1.58. And I don't know what the other dimensions of these other ones are. I think they're all less than 2. Oh, the one on the bottom right, that's a 3-dimensional analog of the Sierpinski triangle. I forget what that's called, the Sierpinski pyramid, maybe. That I think does have a dimension of 2, just by coincidence. Even though it lives in 3 dimensions, you can calculate its Hausdorff dimension. It turns out to be 2. So fractals can have integer dimension. Most of them don't, though. I'm pretty sure that all these other pictures have dimensions that are not integers, and I think they're all less than 2. I think they're all between 1 and 2. They all sit in a plane, so their Hausdorff dimension has to be less than the topological dimension, which is 2 in this case. So I think they're all between 1 and 2. And anyway, and broccoli. I mean, this isn't just a mathematical curiosity. One thing I think is fascinating about fractals is that fractals are the rule, not the exception. I mean, most of nature involves fractals. Coastlines are fractals, and broccoli is a fractal. I think this is, I'm not sure. Maybe this is a CGI picture, but this might be a 3-dimensional fractal. But broccoli, if you took a microscope and looked up close at a piece of broccoli, it would actually look a lot like this. And the structure of broccoli is a fractal. And ferns are a fractal. And mountains and coastlines are fractals. I think Mandelbrot said it really well when he wrote his book, The Fractal Geometry of Nature. He said clouds are not spheres, mountains are not cones, coastlines are not circles, and that's all true. All those things are fractals. They all have a non-integer dimension, non-integer Hausdorff dimension. So they're more the rule than the exception. And I know it seems strange to have dimensions that aren't integers. I'm not going to go into the mathematical details of how to compute Hausdorff dimensions. I do that in my video on fractals. But just suffice it to know that there are things in nature, and they're the rule, not the exception. Most things in the natural world have a non-integer dimension, which I think is pretty amazing. And a classic example is the Mandelbrot set. Turns out the surface, and I talk about the Mandelbrot set in 2 other videos, and it turns out that the boundary of the Mandelbrot set has a Hausdorff dimension of 2, which really surprised me when I first learned this, because I think most, maybe not all, but I think most 2-dimensional fractals in the plane, most fractals in the plane curves, they have a what is it called? Topological dimension of 1, but a Hausdorff dimension of 2. I always assume that all such curves were space-filling curves, meaning that they fill up a finite region of the xy plane. It doesn't really look like the boundary of the Mandelbrot set does. So maybe it does. I don't know. But it does have Hausdorff dimension too. That I do know. And I've made several videos on the Mandelbrot set. This is just a zoom in on part of it. It is fractal, and one property of fractals is they're self-similar. They have similar structures on all distance scales. You can zoom in as far as you want in any portion of the Mandelbrot set. It keeps still having, a lot of the same features, even a lot of new ones. Pretty amazing. But yeah, here's a Julius set. These are closely related to the Mandelbrot set. You can kind of think of the Mandelbrot set as an encyclopedia of all possible Julius sets. I mean, if you zoom in on the region of the Mandelbrot set that corresponds to the value of C that you use to define your Julius set, then you see the same kind of structures. Pretty amazing. So anyway, yeah, a mini Mandelbrot set inside the big Mandelbrot set. Like I said, it's self-similar. It has infinitely many copies of itself, but it seems to have a lot of other structure to it as well. So anyway, that's my video. That's my video on higher dimensions. I hope you enjoyed it, and I'll see you next time.